Good morning, everyone. Welcome to the EasyPower Tuesday Refresher Series. My name is Jim Chastain. I'm an applications engineer here at EasyPower. And today we're starting the first part of a four-part series that we call Introduction to Protective Device Coordination. There is a lot of interest in updating coordination, especially with the emphasis now in the National Electrical Code. And we hope to cover this in a 4-week process. And today we're going to focus on primarily the tools and the loads that we need to be protecting. And as we are in the habit of doing, we'd like to start with a poll question. So if you would please participate and correspond utilizing the feedback on the screen. First question is how long regarding the systems that you're familiar with, how long has it been since coordination was checked or updated in those facilities? And so there's no liability or downside. It's just strictly some feedback that hopefully I'll be able to incorporate in the message or the information that we're providing. And it looks like we have pretty healthy participation today. Let's give this another 5 seconds. Thank you for your feedback. Here's how folks have weighed in on this. And so the issue here is what affects the coordination, and if nothing's changed, why do we need to check it? And we'll kind of touch on that as we get farther into the discussion. And the second question is, have you been involved with a facility that experienced a equipment failure that potentially was due to the result of miscoordination? And this is more out of, again, interest on my part in experiences that the audience has had. And some of the failures could be relatively expensive and prohibitive in terms of both the cost of the equipment and the cost to replace or repair, which puts more emphasis on the topic of coordination. So we got close to a quorum. Let's give this another 5 seconds. Appreciate your attendance today and participating. Here's how people have weighed in on this. And not surprising at all, there's a fair possibility of coordination being a substantial impact on the cost structures. Okay, thank you for sharing. Let's get into the presentation. So our purpose today is primarily to introduce the topic, if you will, and the purpose, and put a special emphasis on the tools that are available. And important among these tools is the need to understand how to utilize the information to the ultimate goal that you want to achieve. So for those of you that have experience, this is maybe not necessary to cover in the depth that we're going to go into, but hopefully even for those experienced in the topic, there'll be information that you're not fully aware of. So the purpose of protection is to prevent damage to the equipment, and this is caused by temperatures either in the conductors themselves or to the equipment. And so we're trying to minimize equipment damage, potentially reduce the risk of fire and explosion in the equipment or the facility where people may be in the area. There's also a potential need to meet legal requirements, especially in safety backup systems or emergency equipment. And then oftentimes there will be a benefit in meeting insurers' requirements for protection of the facility itself. Now, the topic of coordination is, and specifically selective coordination, is a study of the equipment to determine the optimum device settings such that if it's coordinated, we achieve a minimum circuit interruption for different types of faults and magnitudes, and this will allow the equipment or the facility to stay up for the most part and isolate any fault or equipment that's faulty in the most efficient way. Now, the catch-22 here is that often selective coordination will result in higher arc flash incident energy in some parts of the plant, because what we're talking about is a separation in time between the activation of equipment downstream and upstream, where the upstream needs to be slower as a result. So a case in point would be a typical radial distribution system like this, where we have a potential for a fault in one of the downstream buses or downstream loads. And if we, let's say, experienced a fault in this particular bus or equipment, then that fault current would be sensed or felt by at least 3 protective devices: the feeder breaker in the fault line itself, the main breaker of the switchboard or the distribution panel, and then the primary protection for the whole plant or the substation. Now, because this fault is going to be substantial compared to the normal load current, any of these 3 devices would be potentially tripping. And so the problem is, how do we, and if the main breaker trips, then all of the loads on the distribution panel will go down. If the primary fuse is tripped, then the whole plant goes down or the whole substation goes down, and it may be unnecessary or have been unnecessary had we properly coordinated the system. So again, what we're trying to do is to isolate the fault control and make sure that this device clears the fault before the 2 upper protective devices are activated. Now, the most important tool, or the most utilizable tool for this process, is what we call time current characteristic plots. And they have been in use for as long as there have been protective devices. And they, for those that haven't used them much, they present a little bit of a dilemma because they're somewhat different from what we're used to. We're used to having charts or graphs where we have time along the horizontal axis. In a time current characteristic plot, time is in the vertical axis and amperes or current is in the horizontal axis. Most of the elements that we're going to be looking at are considered to be inverse reactions, which means the higher the current, the faster the device will respond. The shape of the data of the plot itself is determined from the data sheet, and so consequently it's important to accurately record the manufacturer's part number and the type, style, and size of any device that we're going to be adjusting or analyzing. Probably one of the more important in terms of the cost of replacement or repair are the power transformers in our plant, which in many respects are going to see virtually every fault that occurs downstream. And so we have an interest in protecting them from overloads, internal faults, and through faults. Now, transformer damage curves only deal with through faults and not internal faults or overloads. In other words, if you have an internal fault, the transformer is already damaged, and so having equipment that's going to protect us against that is going to be useless. So the typical display of a transformer protection, at least as defined by ANSI, is a through fault damage curve based upon the 100% possibility or the probability that there will be damage to the transformer itself. So this is referred to as the damage curve. The upper area in current, actually the lower current but the longer time, is based upon the potential for thermal damage to the insulation and the windings. The lower part, which is the higher current section, if we look at the current on the bottom axis, is to prevent mechanical damage. And this is because of the high current through the windings can physically force the windings apart. And if that happens a number of times, there's a greater probability of mechanical damage to the transformer itself. Now again, this is for through faults, and in this particular case, this is defined in ANSI C57.109, which describes transformer damage for oil-filled transformers. Now, there is this hook in the bottom section. This is what separates the frequent versus infrequent faults as defined by the standard. And so the mechanical damage, although we try to prevent it altogether, there's a potential for some experience or potential for the current to be exceeding this particular limit any number of times. And this is again defined in the standard, and both in terms of the single phase or three phase size of the transformer. And so for smaller transformers, the frequent fault limit is 10 excursions, and the larger transformers and higher MVA, it's defined as 5 faults. And so that shape of the curve is based on the category, the transformer impedance, and the overall 100% damage curve. So now there comes a time when we're protecting delta Y transformers, and it's necessary to understand what the potential source of the damage is, as seen by the secondary winding. And so this difference occurs in single line to ground, and the fact that there is a difference is based upon the correlation between the phase windings on the primary and the phase windings on the secondary. So the winding damage in a through fault is a function of current going through any one winding. Again, that's why we use phase monitoring. But we must adjust the damage curve to compensate if we're talking about primary protection. And so this comes into play when we're looking at specifically in a full load three-phase fault situation. The primary current, if we're looking at the phases, corresponds, at least in magnitude, to the current in the secondary phase current. The problem comes into play when we have a single phase fault or a line to ground fault in the primary, because that one winding fault will be sensed by 2 phases in the primary side. And again, this is only for primary monitoring and a single line to ground fault on the Y side. But what this results in is we only see the fuse in the primary side will only see 58% per unit of the current in the secondary winding. So in our correction scheme or our protection scheme, we need to account for this offset in the damage curve. And so you'll see in the tools we have a second curve then, and in EasyPower the dotted line is the 100% damage curve, and the solid line is the 58% derated curve. Again, it only applies for ground fault protection on the secondary side and ground fault on the secondary side, and the protection installed on the primary side. Then we need to take into account the recommended requirements for transformer protection based upon the installation conditions in terms of the location, whether or not the equipment's being monitored by qualified people, and the voltage level that the application's installed, and then the impedance ratio of the transformer itself. And so these are the percentage of full load current that the protection needs to take into account for each one of these installations or conditions. So what we'll see is when we get into trying to size up protective devices for the transformers, we need to take into account the potential for exceeding the mechanical damage curve, the full 100% damage curve, and at the same time not have the protective devices sensitive or set so low that they are affected by the inrush when we first magnetize or energize the transformer. And so the transformer protection must ride through the inrush, which means it won't respond to an excursion that is represented by this little dot, and it's based upon some assumed variables or multipliers of the full load current. Usually it's 8 to 10 times the full load current for 1/10 of a second, and this is based upon the self-cooled rating. So what I'd like to do is to jump into EasyPower and kind of show how these controls are adjusted and make sure that you're aware of your ability to control these. So first of all, this is the plot for this particular transformer. It's a 1.5 MVA transformer with a 13.8 primary and a 480 secondary, excuse me, a 2.4 kilovolt primary and a 480 secondary. And the tool will calculate the full load current, in this case, on a 480 volt reference. And this is based upon the full load current which is equal to the MVA rating or KVA rating divided by the voltage and divided by the square root of 3. So that'll give us the full load current, which is up here at the top. And as we isolate on that or put the cursor on that, you'll notice down here at the bottom, it tells me what the coordinates for that particular cursor location is. And that will be something very near to the 2250 full load current amps. Again, this is in a 480 volt environment. So the 100% damage curve is calculated, and if we so desire, we could look at everything with reference to the 2.4 kilovolt voltage by right-clicking in EasyPower and setting the reference for TCC scaling on this bus, and we see everything shift, in this case, to a 540 amp full load current. And now this is going to be based on the 2.4 kilovolts, but we still have the same 100% curve. It's just shifted to the left. I'm going to go ahead and put it back to the 480 volt reference. Now, although I have my notes in here, I'm not displaying the frequent faults or the 58% damage curve, derated damage curve. We are showing the inrush, which is a factor of the parameters that have been entered in the setup for the two-winding transformer under the TCC curve. The magnetizing inrush in this case is being plotted at 8 times full load current and 6 cycles. Now, if we wanted to adjust that, if we wanted to see what the difference would be with, let's say, 12 times full load rating, you can see that plot moves to the right, and that will have an impact on protective devices that have sensitivity at this particular time point. And again, these can be set by supervised and unsupervised selection. We've selected the ANSI standard C57.109 for the plot of the curve, the definition of the curve. If we want to show the frequent fault curve, again, the 100% damage curve is the straight line, and that's something we don't want to exceed at any point in time. If we implement or apply the frequent fault curve, you see it takes the recognized Z curve, and so the frequent fault is this lower section, and the vertical bar is just the connection between the two plots. And then if we're going to be considering a single line to ground fault on the secondary from equipment in the primary or protective devices in the primary, we plot the unbalanced derating curve, and we get our second derated plot. So it reiterates the point of making sure, so the full load current is based upon the fan-cooled MVA, and so that's why we're using the 2250. The inrush and frequent fault is based upon the self-cooled ratings. Okay, so when we get into protection, we'll be making sure, one, that we're looking at the right curves, and two, we're applying the correct type of fault for that particular function. And again, the 58% derating curve is only for primary protection of a single line to ground fault in a delta Y transformer. So I'm going to close this TCC, and if we wanted to, we could save it. And let's look at the same setup for a motor. So a motor, again, can be a relatively substantial cost to either replace or repair. And so understanding its operating region and areas that we need to either protect or not respond to are plotted based upon the parameters that were set up when we originally instantiated the motor itself. The characteristic chair shape is built upon the full load current being the top vertical section. So anything to the left, any time current plot to the left of the red chair would be considered a normal start. The horizontal length of this line between the locked rotor amps and the full load current is referred to as the acceleration time. And then this tail is the asymmetric offset. When we first energize, it's somewhat similar to the inrush. Now, all this is related to the setup that we used on the TCC plots for the motor itself. So first of all, we're plotting a full load across the line starting current. If we looked at a reduced voltage, which might be a soft start or another type of starter, we would see a different shape plot, a lower current for the locked rotor multipliers. Again, the locked rotor multiplier is a function of some multiple of full load current, and if we used a different one, it will change the shape of our motor, of our curve, and affect the protective device settings that we're going to be ultimately trying to achieve. So let's take that back to 6. Likewise, the asymmetric offset is a multiplier down here. Typical is in the 1 to 2 range. If we have a different understanding of the motor specifically, or if a different policy for a design, we would use a different factor for asymmetric offset. The stall times now. So this is, again, a normal starting curve. So anything to the left of the chair, any time current plot to the left of chair would be considered a normal start. Any time current plot to the right side of the chair would be considered abnormal. There is a limit that we want to make sure we never exceed, and that's called the thermal limit curve. Once we check this box, then we can show the stall time by this short stubby plot. And as we're setting our protective devices, we want to make sure we don't allow the current and time to reach a point up to or to the right of this particular plot. Okay, so then the task then becomes making sure we have properly characterized the motor itself when we set it up, and then we're given the target range for operation and protection on the TCC curves. All right, so what we've primarily done is emphasize the TCC plots in EasyPower. We've want to make sure that we understand the procedure to minimize the damage to the equipment and defining our coordination policy, recognizing that in fact there may be some impact on instant energy calculation, and we'll be able to explore that when we get into the tool use. It's important to make sure we have the proper protection on the transformer, and then our data entry is primary importance because the TCC plot is based upon the data that we've utilized. So next week we'll be getting into utilizing fuses for coordination and the requirements that are listed in the National Electric Code for series coordination and alternatives based upon the level of current we have coming in from the utility. Thank you for attending today. We look forward to talking to you next week.